All right, so we're starting Unit 3, okay, and we're going to start off Unit 3 by looking at probably the most important part of physics, and that is energy. Okay? Nothing in physics happens without it. Nothing happens, period, without it. Nothing happens without physics either, by the way. Physics is the root of all other sciences, in case you were wondering. Okay? Chemistry deals with the atom. Physics discovered that. So chemistry is applied physics. And biology deals with living things which depend on atoms which were discovered by physics. So biology is applied chemistry, which also makes it found out by physics. You can tell all your other science teachers that. They already know, but they don't like to admit it. All right, so energy is the most important thing, okay, because nothing happens without it, okay? We have to have energy in order for anything to occur. All right, so that's what we'll be looking at, kind of some of the ideas of energy, because energy is, in terms of science, a relatively new idea, okay? It wasn't something that people could describe very well, and it wasn't something they could really demonstrate either, because energy isn't material. Okay, for chemistry, it's easy. We deal with matter, and matter is material, and it's there, and we can see it. Okay, we can make it do things. We can physically measure it. You can't physically measure energy. Okay, it's not material. It's not there. Okay, and so it acts differently. It behaves differently, and thus it's harder to show people. All right. Now with modern technology, it's a little easier, but back, okay, when they were trying to quantify and explain the idea of energy to people, it was very difficult because it wasn't something they could show them. Okay. All right, so simple energy conversion could be something like what you see in this picture here. Okay, these people are doing what is called the Inuit blanket toss. Okay, the Inuit used to use this in order to see over the horizon. If you've ever been to the tundra, okay, it's an Arctic plain. There's no trees, there's no mountains, there's very few hills or anything like that. It's just flat. Okay, and so if you're trying to hunt, like let's say a herd of caribou or something like that, okay, you can't sneak up on them because they see you coming. There's nowhere to hide. So what you want to be able to do is see where the herd is, even if they're over the horizon. Okay? Normally, if we want to see a little bit further, we just go up a little bit higher. But how do you do that if it's just an open plain? There's nowhere to get higher. So what they would do is they would put the smallest person in the group on the blanket, and they would throw them up in the air as hard as they could, okay, and as high as they could. And that person's job would be to look at further because they could see farther and locate the herd, so it would be easier to kind of surround them, hunt them, and then take one out. Okay, so the idea of the blanket toss, or the sort of the physics behind it, is energy conversions. Right? When the person is standing on the blanket on the ground, they have no energy. Okay, they can't fall any lower; they're already on the ground. Okay, they are not moving, so they don't have any energy of movement, right? But when the people holding onto the blanket start pulling on the blanket, they're converting the chemical energy stored in their bodies into mechanical energy through their muscles. Okay, that mechanical energy gets transferred to the person on the blanket. Okay, we call that process work. Okay, doing work means to transfer or change mechanical energy. So we change the mechanical energy of the person on the blanket by increasing their speed. Okay, we get them going really, really fast to the point where they leave the blanket. Okay, once they leave the blanket, they start slowing down, but they are moving upwards. Okay, they're converting one type of energy, kinetic, into another type, potential, as they go up in the air. Okay, as they get to the highest point, okay, they would have no kinetic energy, and then they would begin falling back down, turning their potential energy back into kinetic, speeding up as they fall. All right, so there's a whole bunch of energy conversions that go on in something as simple as I'm throwing somebody up in the air with a blanket. Okay, so from a physics perspective, there's a lot going on there, a lot more than we can see. Okay, and again, can you see those forms of energy? All we see is the result of that energy. We see its result on material and matter and objects, okay, but we don't see the energy itself. And that's what made it hard to quantify for a long time. All right, so big thing here, guys, is, okay, the definition of energy. Okay, energy is the ability to do work. Okay, that is the strictest definition of energy, and you definitely need to write that down. Okay. Energy is the ability to do work. Okay? And I just said a few minutes ago that work is required to change mechanical energy. So it's one thing then the other. Right? I can't do work if I don't have energy. Okay? but how do I get energy? I've got to get it from somewhere, okay, kind of a thing. So if your parents woke you up this morning and said, hey, go out and shovel the driveway, okay, and you went, oh, I don't want to do that, I don't have any energy. First off, you're lying because you can talk, you have energy, okay? You know, if you didn't have energy, you'd be dead, okay? But the truth of the matter is that if you didn't have any energy, you'd be absolutely right. You would not be able to shovel the driveway because you wouldn't have the ability to do the work that shoveling the driveway is. Okay, everyone kind of follow me there. All right, why do we consider shoveling the driveway work other than it's unpleasant and we don't want to do it? Exactly, we're moving something, okay? We're doing work on the snow. We're changing its position, okay? We're changing its location, we're moving it around, okay? All of that requires us to exert forces, lift things, all that kind of stuff. All of that is considered to be mechanical work, okay? All right, so that's one kind of energy, okay? Like work and energy, okay, that kind is all mechanical, but there's all kinds of other types of energy as well, all right? So that's what we're gonna kind of look at here, okay, is some of the different kinds of energy, right? But like we said, energy is difficult to describe because it involves an abstract idea and again, not a material object, okay? Experimental evidence has supported the theory that heat is also a form of energy. In fact, that's not entirely correct, okay? Heat is actually a transfer of a type of energy. What type of energy does heat transfer? Thermal energy, exactly. Okay, people get heat and thermal energy confused in that they think they're the same thing. Okay, heat is to thermal energy what work is to mechanical energy. Okay, work is a transfer of mechanical energy. Heat is a transfer of thermal energy. Okay, they both involve movement of the energy from one place, person, object, system to another. Okay. All right, so we know that energy can move from one place to another. We also know that it can change from one form to another. We use this all the time in modern society, okay? We convert all kinds of different forms of energy into something else, okay? How many times have you pulled out your phone today? A lot. You probably would shock you if you actually sat down and thought about it and counted it, okay? But every time you turn it on, you're converting electrical energy into light. Okay, we don't even think about it. It just happens. Flip on the switch, electrical energy turns into light and heat. Okay, you turn on your car, chemical energy turns into heat, which then turns into mechanical energy and drives the car forward. Okay, we transform one form of energy into another constantly. Okay, right now, me just walking around, I'm doing that. I'm turning chemical energy into mechanical energy and heat. Okay, just by moving around. Right? So there's always energy conversions going on, so much so that it's mind-boggling if we try to track them all. All right, so looking at different kinds of energy here. Okay, the first kind we're going to talk about is the one that we use most often. Okay, much to the chagrin of environmentalists, we use this one all the time, chemical energy. Okay, chemical energy is energy that is stored in the bonds of chemical compounds. Okay. And it is a form of potential energy. Okay? Chemical energy is potential energy. When we release it by burning things usually, okay, then it can turn into other forms of energy like heat and light and such. So this stuff right here, C3H8, we talked about that back in the chemistry unit. That's propane. Okay, that's the stuff that we use in a barbecue or that kind of thing. Okay, the molecule itself looks like, sorry, I'm going to redraw that because I've kind of scribbled on it here. Okay, the molecule propane looks like this. So we got 3 carbons and we have 8 hydrogens. Okay, everywhere where you see one of these little lines, okay, so between carbons, between carbon and hydrogen, that's a chemical bond. Breaking those releases energy. And that's what we do when we burn propane. We break those bonds, okay? We break those bonds using this reaction, okay? We react propane with oxygen, and in the process, okay, we shatter every last one of these chemical bonds, okay? And as a result, at the end, we have carbon dioxide and water. So some of those bonds reform, but when they reform, they're in a more stable, less energetic configuration. Carbon dioxide and water is a more stable, less energetic configuration. It's called entropy. You'll learn about it in Chem 20. Okay, but that process releases a great deal of heat. Right? So chemical energy is typically used to generate heat, right? And then we can use that heat to turn into other kinds of energy. It's not really efficient, but that's what we do. Okay? So the earliest alchemists realized this. When you burned wood, it got hot. Not obvious at all, but that's what happened. Okay? So when you burned something, it got hot. So they said, is that true for everything? And obviously it's not, because not all things burn. And not all things burn at the same rate. They found that some things burned hotter than others. Okay, and we know that. Okay, certain types of wood burn better than others. Okay, if I was to have a choice between heating my house with wood or coal, which one would I choose? Coal. Coal burns a lot hotter than wood does, and I would use a lot less of it. Okay, so there's a difference in fuel. They called these back then the hidden secrets that were inside of chemical reactions. Okay, I don't know why they called them that. It made them sound important, I guess. Okay, but they found out that some things had more of these hidden secrets in them than others. Okay, again, that's what we call in the modern sense entropy or enthalpy. Okay, it's how much energy is in there. Okay, and everything was a little bit different. Okay. If you mix certain chemicals together, you could obviously produce surprising results like gunpowder. Okay, and the discovery of gunpowder, that's a highly energetic reaction. Okay, things of that nature. All right, it was Antoine Lavoisier who realized that equal amounts of different substances when burned actually did produce different amounts of heat. He actually scientifically measured it. Okay, and he made it basically a chart of fuels and their quality. Right? This fuel releases this much energy per gram. This one releases this much energy per gram, okay, and so on down the list. Okay, and it essentially created kind of a supply and demand for high energy fuel. All right, so when we burn wood, okay, the energy in the cellulose molecules, okay, is released and it's turned into heat, okay, and the end products of that are water vapor, okay, carbon dioxide, particulate smoke, okay, things like that. Right? So chemical energy is the potential energy stored in the chemical bonds of compounds. Okay? The food you eat contains chemical energy, and your body breaks that down in your cells. Okay? It's part of the job of the lysosomes. It's part of the job of the mitochondria, mostly the mitochondria, okay, that we're breaking those bonds and releasing the energy stored in there. All right? So chemical energy is a form of potential energy, okay, and we're getting those that energy from the bonds in the molecules. All right, questions on chemical energy? Okay, now electrical energy is another one. Okay, this picture of this thing here, okay, that's the first battery. It was invented by Alessandro Volta, an Italian scientist, okay, who discovered that electrons can move and flow through a wire, right? And so as a result of that, he was able to essentially create this stacked series of metal plates, okay, where electricity or electrons would flow from one end to the other, because there was a potential difference in the electron nature, okay, between the bottom of the cell and the top of the cell, so electrons would flow. Okay, this is the ancestor of the modern AAA battery. Okay, the very distant ancestor, but that's what it is. Okay, it would have generated less electricity than a AAA battery and been about this big. Okay, about that tall, probably about that big around. Right? But it was the first battery. It produced essentially a portable energy source. Portable, not by our standards, but portable then, because you didn't have to carry around a big boiler. Okay. All right, so electrical energy is the work done by moving charges. So when electrons flow through a circuit, they move very fast. As they go through whatever device we're using, they slow down. Okay? It's called resistance. Okay? If something is highly resistive, it's going to get very what? Hot. All right. So if you made toast this morning, okay, when you put the toaster down, right, the element inside glows. That's because the element is made of a metal that is very resistive to the flow of electrons. So as the electrons go through, it's hard for them to go through. They get slowed down. Their kinetic energy of how fast they were moving before turns into heat. Okay, and that element glows, and that heat is then used to toast your bagel or toast or whatever. Okay, the same was true for the old-fashioned incandescent light bulb. Okay, that would be the kind that had the filament inside. Tungsten, which is what the filaments were made out of, is a very poor conductor of electricity. So poor that when you try to run electricity through it, it glows white hot. Okay, incredibly hot, right? And so it makes a lot of light, but it also makes a lot of heat. Okay, incandescent light bulbs are not very efficient, right? a 60-watt light bulb, okay, uses 60 joules of energy every second. And most of that energy is heat. Very little of it is actually light. Okay? Incandescent means to produce light through heat. Okay? So it's not an efficient use of electricity, which is why we now replace a 60-watt incandescent bulb with a 4-watt LED. Okay? LEDs, you can have them on for hours. You can reach up and just grab and unscrew them from the light. Okay? You have an old-fashioned filament light bulb on for about 2 seconds and you can't touch it. Okay? It's too hot to the touch, it'll burn your fingers. All right, so okay, a lot of difference there in the ability to conduct electricity. All right, so electrical energy is the work done by moving charges, so it's actually a form of kinetic energy because it has to do with the movement of something. Okay, so obviously Alessandro Volta contributed a great deal to the science of electricity, hence the units for electrical power are named after him, volts. Okay, that's where that came from. All right, so his battery was essentially moistened paper, okay, between stacks of different metals. Okay, different metals have the different abilities to conduct electricity, so electrons would flow through them. Okay, and that created a very low voltage battery. Right. All right, now electricity and magnetism are very closely related. Okay, if you have like a very high voltage wire, around that wire there will be a magnetic field. Okay, there will be magnetic effects. Okay, there will be an electrical field, but we can also create magnetic effects with electricity, and vice versa. Okay, those two forms of energy are very closely related to each other. It is in fact possible to force electrons to travel through a wire using a magnet. Okay, this was discovered, okay, by Faraday. It's the first generator. Okay, all this generator does is push the wire or push the magnet through this coil of wire. Okay, when it pushes the magnet through, the electrons are a bit repelled by this magnetic field that's around the magnet, and it forces them to travel through the wire, generating a current. Okay, so essentially, a modern day generator just has a magnet that's passing back and forth through a coil of wire. It's a little more complex than that, but at the most basic level, that's what it is. And that produces what kind of current? Not just electrical, what kind of electrical? Direct or alternating? Alternating, because it's going in, out, forcing electrons to go different directions. Alternating current. Okay, a more direct current has to have a direct constant source. Okay, so that's what kind of Faraday discovered. But okay, a guy named Ørsted also discovered that electricity has magnetic effects. Okay, he was actually demonstrating something to a university class that he was teaching about electricity, and he happened to have a compass that he was going to be using later in the class for another demonstration. He laid the compass on the table, and when he turned on the electrical current, the compass went from pointing north to going parallel to the wire. Okay? As soon as he shut the power off, the compass went back to north again. Turn the power on, and it would go parallel to the wire. Okay? Meaning that around this wire, there was a magnetic field. Okay? And the compass aligned with that magnetic field. Okay? It was at that point that we discovered electricity produces magnetic effects, and magnetism can produce electrical effects. Okay, everyone kind of follow me there? Okay, and we see evidence of that all over the place actually. Okay, the Earth has a magnetic field that protects us from, you know, a lot of the harmful radiation and charged particles that the sun spits out all the time. Okay, and we see that, okay, when stuff hits that magnetic field, it slows down, and when stuff from the sun hits the Earth's magnetic field, it slows down, and we see what? Northern lights, exactly. That's what causes the auroras. Okay, we see the effect of magnetism on charged particles in that it slows them down, it makes them glow. Okay, and we see that light energy as the auroras and things of that nature. Okay, everyone kind of follow me there? Okay, so all kinds of different effect between these two types of energy. All right, so Hans Ørsted, okay, is the guy who discovered that an electric current can produce magnetic effects. So underline that, he's important. And then Michael Faraday did the opposite. Okay, he passed a magnet through a coil of wire and observed that that causes an electric current to flow through the wire. Okay? Again, just examples of how easy and common it is to convert one form of energy into another. Okay? Now, something to know though about these conversions. Anytime I convert one form of energy to another, am I going to get all of it? Never. Okay, there is no situation where 100% of one type of energy will be converted into the other. Okay, energy is always lost at any energy conversion. Okay, and you'd be surprised just how much of it is lost. Okay, near the end of this unit, we're going to do a very simple lab where we run a cart down a ramp and we compare the energy at the top of the ramp to the bottom of the ramp. The ramp is just over a meter long. In that 1 meter, you will lose between 1/2 and 3/4 of the mechanical energy there was at the top. Okay, and it's just a simple thing of running a cart down a ramp. Okay, no energy conversion is 100% efficient, and very few are even anywhere close. Okay, which is why we're looking more critically at how we generate electricity. The more conversions we have from our initial source of energy to electricity, the less efficient it's going to be. So we want to try and eliminate a lot of the intermediate energy conversions, because we know every time we do that, we're losing some energy. Okay. All right. Okay, so we got Oersted, we got Faraday, okay, and then we got this guy down here, Seebeck. Okay. Seebeck discovered you can actually turn heat directly into electricity. It's not very efficient. We don't use it for very much, except for like making circuit breakers, okay, or using thermal couples. Okay, a few things we'll use thermal couples. We'll talk about kind of what things do. Okay, but he invented essentially what is the first thermal couple, which is a device that converts heat energy directly into electricity. Right. What he built is basically this apparatus here, which had an iron bar. And then on top of that iron bar, kind of soldered to it, okay, was a piece of copper, okay, and then he had a compass needle in between them. Right. Now, when he started this out, the compass needle is pointing north. Then he puts a heat source on one end of the iron. Now, when you start heating up this end of the iron, okay, heat wants to flow from here to there. Okay, what's that process called when heat flows through a solid? Conduction. Okay, not all things conduct heat the same. Okay, iron is a poor conductor of heat, copper is better. Okay, so as that heat energy is trying to flow from one side to another, it's moving the particles around, including the electrons, and you start to get this flow of heat. Well, with the flow of heat comes a flow of charged particles, an electric current. Okay, it doesn't produce much of an electric current, but it's enough that the compass needle will orient itself parallel to the apparatus. Okay, proving that, yeah, just heating this up is causing a small electric current to be formed. Okay, so like I say, a few of the places where we would use that would be like in circuit breakers. Okay, in your house, how many people have seen the electrical panel in their house? Okay, if you run too much electricity through the panel, then the breaker will pop, right? Everything's connected to that circuit, then goes off. Okay, the way that that works is essentially it detects if there's heat building up in the circuit, and heat builds up in a circuit if you're drawing too much power through it. Okay, so if this circuit gets too hot, enough of a current is formed that we can use a small thing to pop the circuit open. Okay, that will stop all flow of electricity through the circuit, and the circuit will cool. Essentially, it prevents electrical fires in your house. Okay, before there were circuit breakers, we used fuses. Okay, fuses just had weak metal inside part of the circuit. Okay, and as that circuit got too hot, the metal would melt, and then that metal would drip, and the circuit would be broken. All right, we called it blowing a fuse. Okay, usually when that stuff would happen, the glass that was enclosing that thing would break, okay, and then you would have this broken circuit, and no electricity would flow through. Okay, but we have to do that because if we don't, circuits can overheat and cause electrical fires in the house. It's a type of thermocouple. Okay, another place we use it is in some models of hybrid cars. Okay, some models of hybrid cars have thermocouples embedded in the brake rotors. Okay, so if you've ever looked inside of a wheel, okay, on disc brakes, there's a big shiny rotor, okay, and then there's a clamp. Okay, the clamp is the brake pads. They clamp shut onto the rotor, and that's what slows your car down. Obviously, that process is going to use friction and produce a great deal of heat. If you ever watch night racing, you can actually see the rotors of the cars glow when they apply the brakes. It's just cherry red circle. Okay, so it generates a lot of heat. So they embed thermocouples in the brakes, and the thermocouples take the heat generated by applying the brakes and they turn it back into electricity, which they send to charge the battery. Okay? It tries to recover some of the lost energy that you would just waste by applying the brakes. It's not a lot, but it's enough that it's worth doing on most electrical vehicles, or at least hybrid vehicles that have a battery. Okay? Everyone follow me there? Okay? So thermocouples have a use, but it's not something we're going to go, hey, I need to generate electricity. I'm going to start a fire and throw a thermocouple in it and make electricity. It's not going to generate that much power. Okay? But it's enough that we can use it for a few practical purposes. Okay, so that was Seebeck's contribution, the first thermal electric converter or thermocouple. All right, nuclear and solar energy. Okay, 1896, a guy named Henri Becquerel, okay, observed that certain atoms spontaneously disintegrated. Okay, and in that process, they would emit radiation or radiant energy. They would either glow or emit heat or emit harmful well, they didn't know at the time, but harmful particles. Okay, this led to the development of nuclear energy. Unfortunately for people like Becquerel and Marie Curie and those kind of people who were around at the dawn of the nuclear science age, they didn't live very long. Why? Yeah, they all developed cancer because they were playing around with radioactive materials, not understanding and not knowing, not their fault, but they didn't know, okay, that these things were emitting harmful radiation that was essentially poisoning them. Okay, they were very often sick. If you see pictures of all these people, they're like pale and sickly looking, okay, because they were dealing with this stuff all the time. Okay, Henri Becquerel's desk is on display. I think it's at the Museum of Natural History or the Smithsonian or something like that, but it's encased in lead-based glass because it's still radioactively hot. Okay, if you take a Geiger counter to his desk, because he kept samples of all this stuff in his desk, okay, and it absorbed the radiation from these things. If you take a Geiger counter to his desk, it just goes nuts. Okay, his desk is still highly radioactive to this day. All right, so imagine being the guy who sat and worked at that desk. Okay, I don't know, maybe he's still radioactive too. I don't know. Okay, but it's something that sticks around for a very, very long time. Okay, and unfortunately for people, they didn't know that. Okay, we do now. Okay, and so we're watchful for it. In fact, we use this idea of them emitting particles to detect if someone has been exposed to too much radiation. If you work at a nuclear power plant, you get a special badge. Okay, not with your name on it. It's white. Okay, but it turns black the longer you're exposed to radiation because these high energy particles will hit it, and it's essentially like photographic film. It just changes to black, okay, as more radiant energy strikes the thing. It's not something that we can see, but it can slow down these high energy particles when they hit it. And so if you've been working, in the nuclear power plant, and at the end of the day you have to turn in your badge, and if it's dark, you don't come back to work for a while. Okay, my grandfather actually worked at the nuclear power plant where they developed the uranium for the first nuclear bomb, the Hanford nuclear plant. Okay, and he had this badge. Okay, and he worked with a couple of other people there who were the firefighters there. Okay, and several times the firefighters would get sent home, and they'd be told, "Don't come back for a week." Okay, they come back for a week to get a new badge. Okay, and they work for a while, and the badge turns black to get sent home for a week. Okay, they just, every time it turned black, they sent them home. Okay, they're absorbing these high energy particles that we can't see. They're totally invisible. Okay, but they obviously are harmful. Okay, so nuclear energy comes in two types. Okay, there's nuclear fission and there's nuclear fusion. Okay, fission is the type we use most often because it's more easily controlled, especially for using in a nuclear power plant. Nuclear fusion is incredibly powerful, but harder to control. It yields way more energy than fission does. In fact, by comparison, the first nuclear detonations were fission-type bombs. Okay, they detonated in the range of a few kilotons. Okay, which means they had the explosive equivalent of a few thousand tons of TNT. The first nuclear fusion or hydrogen bomb that was detonated was in the range of about 10 megatons. Okay, that's difference of thousands to millions. Okay, so it's way, way more powerful to use a fusion reaction than it is to use a fission reaction. The sun runs on nuclear fusion. All right, we'll talk about that in a few minutes here, but okay, there's two types. Okay, so nuclear energy is a type of potential energy. It is the potential energy stored in the nucleus of an atom. If we alter the nucleus of an atom, okay, as we learned in chemistry, we change chemically what that atom is. Okay, it would no longer be uranium; it might turn into lead, okay, or something like that. But we change it. We change the nucleus. We release the energy that holds the nucleus together. Right now, we're not talking about one atom. We would never notice that. Okay, but in even a small sample of something, there are, well, lots of atoms. Okay, if we start breaking them all, we're talking about a lot of energy. Okay, so if an atom is split, okay, then we have nuclear fission. Okay, if we force two atoms together, then we have nuclear fusion. All of that energy gets released because we alter the atom itself. Right, Hargan? Yeah. All right, so we talked about nuclear fission back in chemistry. I showed you how like a nuclear fission bomb works, right? It has the high explosive, okay, and it goes in and it sends particles towards the uranium and it splits, and then that causes the chain reaction. Okay, for fusion, okay, fusion results from incredible pressures from whatever force we're using to force two atoms together. In the sun, it's hydrogen fusion. Okay, and that hydrogen fusion is caused by the sun's incredible mass. Okay, the sun has a mass of 1.99 times 10 to the 30 kilograms. Okay, it's massive. By comparison, the Earth is on the order of several million times smaller. Okay, this is the mass of the Earth, 5.98 times 10 to the 24 kilograms. Okay, 10 to the 30, quite a bit bigger, right? The sun is almost entirely made of hydrogen. So all of the gravitational pull caused by all of this mass obviously keeps all the planets in our solar system orbiting the sun. But what it also does at a much smaller level is there's enough gravitational force there that atoms of hydrogen are crushed together. Okay? They are forced together by the incredible gravitational force inside the sun and fused into atoms of helium. Okay, so we'll get three atoms of hydrogen. Okay, they'll come together and they'll form a single atom of helium. Okay, and in that process, massive amounts of energy are released. Okay, but it's only because there's so much gravitational pull there. We can replicate the process not through gravity on Earth, but through high explosive. We can create enough pressure that hydrogen can fuse together, and that can create essentially a nuclear weapon. Okay, it's not a reaction we use in a controlled basis for anything. Okay, now obviously we're working towards that, because if we could develop something like that that releases energy but not as heat, then we would have what kind of fusion? Cold fusion, okay, which is, you know, going to be like the savior of all things. Okay, if we can ever get it to work. All right, so that's nuclear energy again, potential energy, okay, and it's stored in the nucleus of an atom. Anytime we alter that, okay, then we have nuclear energy being released. Okay, for a long time though, people looked at the sun, okay, and went, "Ooh, that's bright," and then thought it looks like a big fire, and it is. Okay, if you ever seen like video of the sun, it is. It's a big giant fire in space. But at the time, you know, way back when, they're like, well, fires are caused by burning stuff. Okay, and so they thought the sun was actually a chemical fire, not understanding, of course, that space is a vacuum and fires don't work in space and whatever. Okay, but once they started calculating based on some observations of planets and movements and stuff, the mass of the sun, they figured out that if the sun was actually a chemical fire, it would burn out after 5,000 years. It would have gone through its entire mass. Okay, obviously that's not the case. It was some other kind of fire that doesn't require oxygen. It's a big giant nuclear fusion fire. Okay, and that's what's constantly providing energy, okay, for our planet. Okay, then we have motion and energy. So we have kinetic and potential energy. Anything that has to do with motion and energy is mechanical energy. Okay, mechanical energy results from either the elastic nature of something, the position of something above the ground and its potential to fall, or its actual direct movement. Okay, those are essentially the types or the parts of mechanical energy. Okay, this very simple demonstration here is called a Newton's cradle. You've probably all seen this thing, right? You pull one side and it goes tick, 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 back and forth. Okay, this was how Newton was going to explain energy. He was going to explain the idea of energy. He called it vis viva, or the living force back then, okay, because we didn't have the term energy yet. He built that thing, and then he took it into the village square to show people, okay, and to explain to people energy. he nearly got himself beheaded for this. Okay? Because people said, "You're a witch. Look what you're doing." He said, "Well, this is just the living force of, the stuff that's in here. He said, I pull this thing away, and when I let it go, I transfer my living force to it, and it comes down and it hits this, and it transfers that through all the other little balls, and the other ball flies up on the other. Living force? You sound like a witch." Okay? And he almost got himself beheaded over this, because of course at that time people were very superstitious, and anything made you a witch. It was a good way to get rid of people you didn't like, just accuse them of being a witch. Okay, and well, actually, a warlock. Because a male witch is a warlock. Whatever. Anyway, okay, there was a whole bunch of really bad stuff going on at that time. He had to talk real fast to get himself out of that. Okay, and explain essentially the mechanics of what was going on here. Okay. In so much as he nearly got killed over it all, okay, it did lead to a much better understanding by most people of how this idea of this living force, as he called it, worked. Okay. All right. So motion and energy. Okay. We've seen Newton's cradle. Okay. Another guy came up with a different demonstration. His name was Gottfried Leibniz. Okay, and he reasoned that whatever caused one ball to move had to be transmitted through the balls to the other ones. Okay, and so he called that, again, vis viva, just like Newton did. Okay, but for simplicity, we call it energy. Okay, he also reasoned there were two types that could be observed in nature. So flowing water, wind, or any object in motion could be made to do work because of its motion. If something's moving and it crashes into something else, it'll do work. Okay, so that's kinetic energy. An object above the Earth's surface has the potential to fall. If we let it go, it'll pick up speed and it can do work. Okay, so that would be gravitational potential energy. Now, the thing to remember here, guys, is that potential energy can't do work. Okay, just because I'm holding this pen here and it has potential energy, okay, this pen can't do any work with its potential energy. It can only do work if that potential turns into kinetic. Okay, just having potential doesn't do anything. Okay, it's what you do with your potential. Life lesson. Okay, that means something. All right, so you have to convert your potential energy into kinetic. Okay, the sum of these two types of energy, kinetic and potential, is what we call mechanical energy. Okay, mechanical energy is the most important part of high school physics. Okay, questions on mechanical energy? All right, now heat and energy is the one that was most obvious. That connection was very obvious even from the very start of like the Industrial Revolution and things like that. We were using this idea of thermodynamics, the movement of heat and energy, okay, to do all kinds of things. Before we really understood what was going on, we were able to harness it and make it do stuff. Okay, kind of commentary on society. It doesn't matter why it works or how it works as long as it works. Okay, and that's kind of how the Industrial Revolution went. Okay, so the ancient Greeks knew, they didn't have any concept of energy, obviously, but they knew that they could get heat from certain things. Okay, we move forward to around like the mid 1700s, and Joseph Black observed that when a cold object was placed in a cup of hot water and then removed, the object was much warmer. Crazy. Okay, absolutely crazy. All right, yeah, but it's true. Okay, and that's because heat can be transferred, but it can only be transferred in one direction. You can't transfer coldness. Okay, you can transfer heat, but you can't transfer coldness. And we have a problem with that in our society because we put something in the fridge and we transfer coldness. Okay, but in fact we don't. Okay, when you put something in the fridge, the heat from it goes into the coolant. Okay, if you ever like pulled out a fridge, it's got that kind of grid on the back, and there's a big compressor on the bottom. That's the thing you can hear running, and when the fridge is running. Okay, so the heat from the stuff you put in the fridge turns the coolant from a liquid to a gas. It absorbs the energy, so the heat is transferred from your food to the coolant, not the cold transferred from the coolant to your food. You can't transfer coldness. You can only transfer heat. Okay, or energy. Okay, so he observed that that was true, okay, and that this heat only flowed one way, and that was the birth of this idea of thermodynamics, the flow of heat, okay, from one thing to another, right? And so obviously then we got this idea that heat is not a form of energy. Heat is the transfer of thermal energy. Okay, whereas work is the transfer of mechanical energy. You should probably write that down somewhere. You may have already because I mentioned it before, okay? But work is the transfer of mechanical energy and heat is the transfer of thermal energy. All right, now heat and mechanical energy obviously go hand in hand because anytime things are moving, heat will be generated because of what? If I have two things and they're moving past each other, there's going to be friction. Okay, friction is going to turn mechanical energy into sound, heat, and light. Okay, that's what friction does. It essentially steals mechanical energy. All right, so the first person to kind of make this connection was a guy named Benjamin Thompson, who for some reason later changed his name to Count Rumford. I don't know why. Okay, but he became the Minister of War in Bavaria, and he was in charge of the manufacture of cannons. Okay, back then, manufacturing a cannon was difficult. Okay, you had a bunch of people operating what would look like a very large drill, right? But it was hand operated. It was like an auger. Okay, and they would have a big lump of metal, and they would bore it out with this big drill. Okay, now Count Rumford, Benjamin Thompson, okay, is essentially going to be given credit here for the invention of the coffee break, because his workers would put tea kettles on top of the lump of iron or whatever metal they were using, okay, that they were boring out. They would put a tea kettle on there and they would start boring it out. And after a while, the tea kettle would boil. Just from the friction, okay? From them boring out this lump of metal with a big drill, there would be enough heat generated from the mechanical energy that they were putting in that it could boil a tea kettle, which meant you didn't want to do this during your coffee break and lean against the cannon. You'd like get burned really badly. I'm sure there were a lot of workplace accidents due to that. Okay, but you had to watch out because I mean, if that thing was hot enough to boil a kettle of water, okay, it was obviously raging hot. Okay, and you wouldn't want to touch it. So it probably wouldn't have been the nicest place to work. It would have been hot in there. Okay, so we noticed that a huge amount of heat was being generated into the bored metal. In fact, you could boil a kettle of water on the cannon while it was being bored. Okay. So Rumford suggested that that heat was manufactured by the workers, and it is. It was the mechanical energy of the workers that was creating this thermal energy that he was discovering. So he discovered that heat and mechanical energy were related. So that's Benjamin Thompson did this, okay? Benjamin Thompson or Rumford, this was his contribution. Heat and mechanical energy are related. Okay, a little while later, Thomas Young linked mechanical energy to kinetic and potential. Okay, it was the kinetic energy, essentially, the people moving the drill, okay, that was creating this heat. Okay, so he was the one who basically said it could be kinetic or potential. Okay, and that led to the current definition of energy, which is the capacity or ability to do work. Is it missing? Oh. Oh. Whoops. Okay, well then I'm going to give you a couple minutes to write down the sentences I underlined real quick. Oh, it's terrible. I actually have to write something down. Just do it. Okay, I'll give you a couple minutes on that. Now, the most important person in terms of putting all of these other discoveries together into some kind of scientific or experimental apparatus is a guy named Joule, okay, which is why the units for energy are named after him. Okay, so first off, we had Sadi Carnot, who was a French engineer. He did a bunch of experiments that transformed heat into mechanical energy. That's not an efficient conversion. It works, but it's not efficient. Okay, he discovered that the transformation of heat into mechanical energy could only occur when thermal energy flowed from a hot object to a cool object. Okay, there had to be that flow of energy that they discovered long ago. Okay. But he always noticed that a lot of heat was lost. It wasn't an efficient process. Okay, but Joule, he came up with these two experiments here. Okay, and he showed experimentally with the ability to measure it, okay, that you could convert mechanical energy into heat. That essentially potential energy was a form of energy. So in this first one, he had a sealed jar with a thermometer in it, and he had these blades inside, like fan blades with the holes in them. Okay, and then he had these masses set up on a pulley system so that this whole apparatus inside the jar would spin when he released the masses. Now, these masses right now have potential energy. right? As they fell and the blade turned, the temperature inside the jar would go up. Okay, and showed unequivocally that these hanging masses had energy. It was the only place where the energy to cause all that movement and the change in heat could come from. Okay, he did an even simpler one with 2 blocks. Okay, he just drilled a hole into a stationary block, okay, like a big piece of wood essentially, and then he took another block, he moved it away, and then he just let it fall, and it smashed into the stationary block. And when that happened, the temperature in the stationary block would go up. Okay, you can do this experiment at home. Right? If you take a hammer and a piece of wood, okay, like scrap wood, not furniture, okay, and just hit that piece of wood a few times with the hammer, put your thumb where you were hitting, stop hitting, put your thumb where you were hitting, okay? Yeah. Well, I have to say these things, okay? It'll be hot there, okay? If you if you put a screw into something and then pull the screw back out, the screw's hot. Right? All of this is evidence that mechanical energy of movement is going to turn into heat. Okay, and that's essentially what he showed. Potential energy, any form of mechanical energy, can be turned back into heat. They are actual forms of energy. Okay, or into thermal energy. I keep saying heat, but turned into thermal energy. Okay. All right. Got a few questions here I want you guys to answer. Okay, so the circled ones are the ones I want you to answer. Okay, so we got 2, 3, 4. Is this sheet in your notes? I think it is, right? Okay, so just circle the questions there. So 2, 3, 4, 5, or sorry, 2, 3, 4, 6, 9, 10. Okay, 12, 13, and 14. All right, give you guys a little bit of time to work on that. Hopefully we'll be able to go through it before the bell. Okay, if not, we'll go through it tomorrow.